right, so hello everybody, welcome from all around the world. We're very happy and excited to have you here today for the second keynote for the Software Product Line Conference and the Models Conference. So today's keynote speaker is Krzysztof Czarnecki, and I will introduce him in a moment, and I am Czarnecki from the University of Alberta. So before we start the session, I'd just like to thank all our sponsors for SPLC, Pure Systems, ACM, SIGSOFT, ETS, Metacase, and Elsevier, as well as the model sponsors ACM, SIGSOFT, IEEE, Computer Society, TCSE, Université de Montréal, InQ Labs, and Evado. So thanks to all our sponsors, we wouldn't be here today without you. So today we have a very exciting keynote by Krzysztof Czarnecki, who's going to talk about models and AI-enabled systems for the case of automated driving. So Krzysztof Czarnecki is a professor at the Department of Electrical and Computer Engineering at the University of Waterloo in Canada, where he leads the Waterloo Intelligent Systems Engineering Lab. So his research currently focuses on safety and automated driving systems, but Krzysztof has a long track record and expertise in model-driven software engineering and software product lines with many industrial collaborations and applications of these ideas. In the SPLC community, he's very well known for his generative programming book, which has shaped many of the ideas we work on today. I've personally had the pleasure of working with Krzysztof several years ago, and I learned a lot from this experience. I'm very honored to be here today introducing him, and I look forward to hearing about his latest research on automated driving. So without further ado, I'd like to welcome Krzysztof to the stage. And Krzysztof, I'll stop sharing and the screen is yours for your slides. So let's all welcome Krzysztof from where we are. And
thank you so much. Thank you, Sarah. Thank you to SPLC organizers and models for inviting me. I'm really happy to be here, and I'm so sorry I cannot see everyone and talk as in the old days, but hopefully, yeah, we can catch up sometime in future when those crazy times are over. Yeah. Okay, let me just share my screen. All right. So what have I prepared for today? So what I'd like to do is, I'd like to tell you about, let me start from the first slide. So the title is Models in essentially AI-enabled systems such as automated driving, and I will focus on automated driving. The sort of a more fun title would be the question we could ask where we are on the road to model-driven learned car. And so what we'll try to do is, in this talk, is to kind of tell you where we are actually in achieving sort of full AI self-driving, and what is the role of different types of models, and what are the challenges, yeah, and how we're trying to maybe address them. All right. Spoiler alert, of course, there's a lot of challenges that are unsolved. So the driving task in today's road environment is a very complex task, right? Because essentially we have to understand a very complex environment and perceive it, have sort of environmental understanding, and then make decisions. And we have to deal with lots of uncertainties. So the environment is challenging. I mean, it starts with physics. Perhaps that's something that's best understood with what we can do today with lots of physics and math. There is also the socio-technical system, which is essentially a set of rules that we impose, but it's also all the human behavior or behavior of human road users that's challenging and unpredictable. And we also have the natural environment that is very complex. You know, how do we recognize various types of objects, such as pedestrian? There's basically no fixed rules, right? you can say a pedestrian is someone who, well, has at least a head and trunk, but any part can be occluded, disguised with dresses and so on. So it's essentially, you can only enumerate examples. It's essentially impossible to give any set of sufficient and necessary and sufficient conditions. But then the environment is also constantly changing. You have animals, you have all sorts of objects that can enter the road environment. And even if we try to automate vehicles, for a while there will be human-driven vehicles, but there also will be other road users such as pedestrians and cyclists, even if we had all the other cars automated. So it's actually also a changing mix. We have a heterogeneous set of agents in the system. So I've attempted to sort of make sense of the requirements, like how you would think about the requirements for the task of driving, and what are the elements of it. So this is a framework that was inspired by Michael Jackson's work on requirements engineering, essentially saying that the driving behavior that represents the requirements on the driving task, or in this sense, if we're automating it, the so-called automated driving system, which is potentially driving the subject vehicle, then the subject vehicle has to adhere to a certain set of contracts. These could be described as the road environment with its structure, traffic, and environmental conditions. The vehicle itself has certain dynamics, physics. We also can divide the driving task into different abstraction levels, and we have various qualities such as safety, comfort, progress, energy efficiency, and courtesy. And many of those goals are soft goals that are quite difficult to formalize and full of rules. So in fact, in the field of traffic psychology, there's been a lot of effort to model the driving task for the purpose of understanding, for example, accidents or traffic safety, but also education. And over years, sort of a standard model that has emerged has at least these 3 levels of control. There's a low-level control that's sort of in milliseconds. It's based on physics. Basically, momentum cannot be stopped. So whatever it's sub-second can be essentially predicted using physics. But then in the area of, let's say, in the range of seconds, we have maneuvers. We decide, for example, to stop at the stop sign, or maybe to yield, or to take precedence. And then we also have decisions that we do at the strategic level. So this would be decisions at the level of the entire trip. So for example, which roads do we take? Do we take the busy roads or the less busy, the scenic roads? So it'd be strategic level decisions. In most of the problems that we deal today at the level of individual system, it's really about the maneuvering and control level. So this is sort of up to 30 seconds horizon. The strategic part, we kind of leave it more to the entire transport system optimization. So this is how much I want to say about the requirements. If anyone is interested in diving into the domain, I've actually spent just over a year creating a set of documents that contain standardized vocabulary for the traffic environment, for the maneuver catalog, and also the basic control tasks. And in terms of the quality, there's a document that describes the various safety requirements on driving and comfort requirements. So it's obviously there are many other aspects that are not covered, but I think it's a good starting place, and it's available online. But essentially, it's a stack of documents, and we need to start formalizing this knowledge if we want to be able to measure and also in a prescriptive fashion control these systems to satisfy our requirements. And I'd like to highlight here this one possible representation that has been developed in the group of Emilio Frazzoli, who is a MIT prof who started actually Newtonomy, one of the self-driving companies. And what they've developed in that context at Newtonomy is this concept of rule books. So just the idea that many of these rules, the qualities that I was listing, could be formalized as essentially scoring functions, but we have to have a rich structure of scoring functions. So here, the scoring functions are organized into sets, and these sets are ordered using pre-order relations, such that at the top, for example, we have the safety of humans. And so this is one possible, maybe organization of the qualities that I was talking about. All right, so this is requirements. Then let's briefly talk about the functional architecture. So what I mean by functional architecture, as in systems engineering, I do not mean the implementation. I will give some examples of how functions are implemented, but I really talk about here what are the tasks that need to be performed during self-driving. So clearly we have to perceive the environment, we have to make decisions, and we have to execute them. And a functional architecture can be seen in that progression from perception, from the sensors on the left, towards decision making and implementation in terms of control. Now there's also a vertical structure that it's about essentially time horizons. So just like in the Jean-Michel's hierarchy, you have the milliseconds to seconds and the strategic trip level time horizons. And I'm going just to pick a few key functions that would be relevant as we discuss how such systems could be implemented. So first of all, of course, we have sensor input with typically cameras, laser scanners, and radars. We also have prior knowledge, a map information that can be seen as sort of a memory of maybe recorded by other cars and aggregated, so that we don't have to discover everything from scratch. And then the perception has sort of three blocks. First, the car has to orient itself where it is, has to understand its movements. So there's a lot of physics modeling involved. It then has to understand the different elements of the static environment. So where's the road, recognize any kind of objects, that are maybe not dynamic, static, like poles and garbage cans and whatnot. And then all the dynamic parts of the environment. So this would be traffic, for example, so cars and cyclists and pedestrians and animals. And we need to not only track or recognize and track the dynamic objects, we have to also predict what they might be doing next by taking all sorts of cues. And we integrate all this information into sort of internal representation, and then we can plan the movement of the ego vehicle, the subject vehicle. And that's typically divided into first deciding what road route we take for the trip, what maneuvers we take at every few seconds. And that can be understood as essentially a traffic game. And then finally, we need to generate smooth, continuous trajectories and implement them using controllers. And in the end, it's just simple steering, brake, and throttle. These are the key inputs. All right. So that's the functional architecture. Now, how do we build a self-driving car? And so here I'm gonna build on a sort of three paradigms that Raquel Utterson from Uber ATG and the University of Toronto has identified. She's one of the internationally top leading experts in self-driving cars, and she's leading the research for Uber Advanced Technology Group. And she essentially observed sort of three distinct paradigms that developed over time. And so the first one, interestingly, using a neural network, it's not a new idea to drive a car, and I will explain it in a minute. But the initial idea was just to use a one monolithic neural network. And what we see today in most of the prototypes that were built by companies and the prototypes that are being tested, the sort of industrial engineering forced a different architecture, which is much more modular, however, has much less learning than maybe the so-called end-to-end driving. So it's less AI. But we see an evolution that points towards more and more AI. So we're kind of coming back to, again, sort of one big, but now maybe modular architecture of neural networks. And a spoiler alert, with actually connections to explicit models that, models in the sense of model-driven engineering that experts can access in order to control the evolution of a system. All right, so the very first paradigm, it's called end-to-end driving. And it goes back to work, for example, at CMU, but also in Germany. So one example is Alvin. So it's a paper from 1995. And this was actually built as a prototype that drove across good parts of US, basically doing what we would call today kind of level 2 autonomy, sort of autopilot or Tesla autopilot style. And it's essentially just a neural network that takes raw input. So in this case was just camera images and outputting steering angle and acceleration. And the method is essentially just to train a gigantic neural network with these pairs of inputs and outputs. So essentially, we can think of this as an example of what's called imitation learning, or learning from demonstration. And that particular type of learning from demonstration is called behavioral cloning. So essentially, it's just supervised learning where, let's say, you first drive a car and just record the images and the input of the driver, and then you just train a neural network to repeat the same thing. And you hope that the neural network with enough data will actually start generalize enough that you could actually let it drive a car. And interestingly, lo and behold, you can actually build a working demo pretty quickly. For example, NVIDIA has built a prototype, and I mean, I actually had a chance to sit in one of these prototypes at the Consumer Electronics Show a couple of years ago. And it was in a parking lot, but still, essentially, there was no driver behind the wheel. And the car was just driven by a end-to-end neural network. Yeah, like I think this was actually pretty brave in retrospect. So the advantage of it is it's just easy, but disadvantage is, of course, that first of all, it's a black box. There's no explainability. If something goes wrong, there is essentially impossible to tell why and how to fix it. And also, the other problem is because it's a monolithic system, it requires exponentially more data to train compared to a modular system. And so there's a nice article that explains that, but the basic gist of it is that, let's say if you have perception just to recognize cars and and the road, and if you supervise it directly, you need much less data if you sort of supervise it end to end, just because the information, for example, that you brake for a certain type of car, would be only causing you to recognize the type of car if the car was maybe in front in the same lane. But if it's in a neighboring lane, the network would just learn to ignore. And if maybe that weird car that normally would be seen in the other lane was in your lane, well, that you would not learn in an end-to-end fashion. You could only learn this essentially if that weird car was actually someday also in your lane, which means that you just need more and more, exponentially more data. All right. Now, interesting, what is interesting is that there actually is technology like the Open Pilot is an open source system, which you can actually buy hardware for that and download the software. And there's many models of cars from Toyota, Ford, Honda, and so on, that this can be essentially installed on. It's with a camera, and gives you essentially something like a Tesla Autopilot Level 2 system. And apparently Tesla uses similar technology. All right, so the next paradigm is what we could call traditional or the first generation engineering stack. So this sort of emerged when Google, after the DARPA challenges in 2009, essentially picked up the pieces that came from these academic projects and said, okay, well, we'll develop a self-driving car, right? And this is what today was, it's basically the Waymo company and their pretty advanced product. And essentially what they've done is to take these traditional robotics components, and the main difference is that they've started to use deep learning for perception. And it's a highly modular architecture. And I'll give you an example of what we've actually built in Waterloo from 2016 to 2018. And it's basically this type of stack, what you would call first generation stack, engineering stack. We've tested this on public roads, but it's a very basic system, with our modest resources at the university that we were able to gather. In the end, the system, we tested roughly on 100 kilometers of driving. We would have, during the test campaign, we would have roughly every 8 minutes a disengagement. And it was not because of some maybe mistakes, but most of the cases because of undeveloped behavior. So, certain things we just did not implement, such as, for example, overtaking a parked car, just because our, for example, detection range was about 40, or is about 40 meters with the existing sensors. And it would be just not very safe to overtake on a 2-lane road with oncoming traffic. But in terms of the structure and the processing, it's pretty much the type of system that, if we had some of the billions that these companies have, we could have developed to similar maturity that we see today for companies like Waymo or Cruise. So let me just explain very quickly what this traditional stack does. So first of all, you can think of it as a sort of sequential processing, where you get the sensors. It definitely relies on maps, so a lot of prior information. So let's say for us, the data that's incoming is LiDAR and camera. Then you've got the high definition maps. Then you have a detector. Detector finds all the dynamic objects. After the detector, you have a tracker that essentially pieces together the detections into tracks or trajectories of all the objects, dynamic objects around, giving them IDs, and also does prediction. So the blue part is essentially the past track, and the green one is prediction, where the other vehicles will be driving in the future, like a couple of seconds into the future, usually 3 seconds we do. And then we have a behavior planner, which is essentially an expert system, so it's rule-based expert system, which is with manually entered rules, traffic rules. And those maneuvers are then implemented by a continuous optimization-based trajectory planner. So essentially, if you say, okay, we want to have a turn here, so then the trajectory planner would get some constraints, and it would find some smooth, nice trajectory that then would be implemented by the controller. And so you kind of see it here, the full representation with the dynamic objects and the planned alternative paths, and then the one with the lowest cost that is closest to the center line would be selected. So that's sort of very sequential. You can essentially develop all these elements separately. The only place where machine learning is heavily used is the detector. Perhaps these days also prediction, but like let's say planning, trajectory planning, it's typically done in a classical fashion with classical optimization-based methods and optimal control. And things like, let's say, state estimation would be extended Kalman filters and so on. So very much physics-based, explicit, expert-built models rather than machine learning. So the advantages is it's highly modular. You can essentially have different departments. Like in our case, we had subgroups that were doing perception, behavior planning, controls, and simulation. And so that's what these companies normally do. Each model can be developed independently. Has the modules have clear interfaces, and they're very thin interfaces. So it's for example, we built this on top of the ROS operating system. So each of these interfaces, there will be clearly defined messages. So what is a trajectory? What is a object 3D object detection? What is a maneuver? There's essentially a dictionary for that. Well, the one disadvantage is lack of reliability and robustness of DNNs. So this is perhaps any machinery built today with AI will have this problem. And it's impossible to build perception today without deep learning. There's just no other technology, so you kind of stuck with this. But the current deep neural networks, if you recall Joshua Bengio's keynote, it's sort of the system one type of unconscious reasoning technology. We have this problem of lack of reliability and robustness. What I mean by that, so by lack of reliability, I mean that our detector, for example, it just sometimes just doesn't detect in a frame a vehicle that it could be even clearly visible. So it means is that it's actually objects that are even in distribution. There is some possibility that they will not be detected, even clearly visible. And lack of robustness, I mean, it's clearly when things are actually out of distribution or strange or anomalous or basically have not been represented by the training data, then they're very likely to be not detected or to be misclassified. So just here as an example to sort of show how brittle deep neural networks are. This is basically just applying CNNs to some synthetic data that we produced to carefully study the impact of different weather conditions on detectors. And so the nice thing about the synthetic data set is that we can have exactly the same scene with different weather conditions. And so in this case, we're just doing semantic segmentation. So we have a base image here. This is the ground truth. So essentially the different colors represent different types of objects or stuff, like let's say road, cars are here blue, dark blue, and you have the sky here, and these are buildings. And then we would have another image which has some intensity of rain. You can actually see the rain streaks. Or clouds or paddle or any combinations of these, for example. And we have done two models. One is that was just trained on a data set of clean scenes. And we have here a model B that was trained on both clean and those with adverse weather images. And if we train on clean, we get a pretty good result on clean. But if we actually look and apply this this model A that was only trained on clean to any of these adverse weather images, you see that it actually deteriorates. So for example, having this wet surface, it completely starts to think that there are cars all over the place. With clouds, it kind of thinks that the buildings are all over the sky. And so this is actually pretty well known that adding any type of, for example, corruptions or noise, if you don't train for it, the networks are just very brittle. On the other hand, if you train them and you stay within, they can actually do amazing things. So I'm always amazed to see how, for example, our 3D object detector in point clouds, LiDAR point clouds, it needs 4 to 5 points on a car, individual scan points, and it can actually detect a car and put a proper bounding box around. It's completely impossible for human to do that based on just a handful of points. Right, so what we would like to, of course, ideally have is if the deep networks would tell us when they are likely to make a mistake. And so one idea in that direction is to see whether the networks could tell us how uncertain they are. And so we have two types of uncertainty that can be estimated. And so we distinguish between aleatoric and epistemic. So aleatoric is the uncertainty that's inherent to the data. So let's say if I have noisy data, like let's say very heavy rain, obviously if I just train with heavy rain, and then I see in the input I see input where maybe my car or pedestrian is behind heavy rain. There is just little information about the actual pedestrian, so there is a high noise in the data, right? So if I just have more, data like that, it's not going to improve accuracy. And the other type of uncertainty is epistemic. So this is lack of knowledge. So this is basically the idea that, okay, if I maybe trained only with cars and then suddenly I have pickup trucks and vans, they won't be detected because maybe the network is really not able to generalize to these other types of cars because they are essentially, maybe there were too few samples, right? So now having more samples of these new types of cars would help to reduce this epistemic or lack of knowledge, epistemic uncertainty. And so these two can be actually formally defined using a Bayesian framework. And so roughly the idea is that you would say that given your training data set, there is a certain distribution of models that could be derived from that training data set. And you could think of this distribution of possible models as a sort of infinite ensemble. And so now if you ask that ensemble, so it's a committee of all these models that you could possibly train from that training data set. If you ask them about any particular input, and if they all agree and say that, well, we are uncertain, then you have high aleatoric uncertainty. And if they all highly disagree, then you have high epistemic uncertainty. And you can actually write this down mathematically. Now, the problem is that, of course, yeah, you cannot create such an infinite ensemble. So what we in practice do, so there are many methods to actually estimate uncertainty. These are called Bayesian neural networks. But one that today is state of the art is to actually create an ensemble of perhaps 5 to 10 independently trained models and treat them as a committee, and essentially you use that as an estimate to make these two questions, pose these two questions about aleatoric and epistemic uncertainty. All right, so here I'm just briefly showing that this can be, for example, done on such semantic segmentation images. So we have an input image, and we have the ground truth. This is the prediction, and here we're showing the aleatoric uncertainty, the epistemic, and here's the combination of both aleatoric and epistemic, which is called predictive uncertainty. And so, for example, aleatoric uncertainty is very, very high on sort of edges of things that are, that could be kind of fuzzy, right? So trees are fuzzy, and so clearly you see that, right? And so epistemic uncertainty, for example, is highlighted for this weird car here. There was an artifact from simulation. So the car is kind of stuck in the wall, and certainly it's something unusual, right? But the tree here is not highlighted. So it kind of makes sense. And then if you take both uncertainties into account, you get this image, right? So that sort of would tell you how reliable the classification into the different categories of each pixel is. So that basically would be a very useful information if that uncertainty was reliable. It's sort of to make it, without going into more detail, the short story is that both the accuracy of a network and the uncertainty estimation, they are reasonable for in distribution inputs. But the moment you actually have very low probability inputs or out of distribution inputs, you've got problem of accuracy, obviously. And for example, network will make mistake and sort of think that this is high, give a high score. And if you also estimate the uncertainty, essentially for out of distribution, the uncertainty estimation doesn't really work well. So you can use ensembles for so-called out of distribution detection, but the overall performance is weak. And literally, so we've tested many methods. We've actually contributed to some incremental improvements, and there is hundreds of papers every year. Like, it's a very, very intensely researched area. And all of what I see is just incremental improvements and nothing that can be actually really used, let's say, to tell a self-driving car that, hey, here's something weird, we haven't seen it in training. So it's out of distribution detection is a basically major challenge. I think that multitasking might help. So basically the idea that the more knowledge we put into networks, not just about the cars and pedestrians, but many different classes, there is a certain effect where the more network knows, the easier it will have a time to actually recognize that something is strange. All right, so that's one big challenge, but sort of coming back, what are other challenges? Oh yeah, and let me just say that how do we deal with this challenge today? Well, we kind of put a so-called safety envelope, and we would have, let's say, something like a occupancy grid, which is probabilistic, no machine learning, and if there's some object, well, don't hit it. The trouble with that is that usually it results in quite conservative policies, like down the stream, because you have to be very careful. And essentially the step of safety envelope only works for the sort of immediate physics-based safety, for sub-second. And even then it's brittle because let's say something like LiDAR, we need LiDAR or radar, you need some ranging capability, or range sensor. And they are susceptible to ghosts. So ghost reflections, for example. And machine learning is very good at recognizing ghost and rejecting ghost reflections, but then you would have machine learning again in your immediate safety envelope. So it's really a big challenge. All right. So what are the other challenges with the Generation 1 engineering stack? Well, we have these small and rigid interfaces. So it was an advantage to do this, clear modularity in the dependent development. But the problem is that, for example, if I decide here that all I give to the behavior planner is the class of an agent, whether it's a car, pedestrian, or cyclist. But for example, I don't add many more attributes. For example, let's say, is it a child, is it an adult? I mean, ideally that would be at least the information you would have. But there's many other cues that actually human can pick up visually and sort of, for example, infer intentions of people and things like that. And you could use machine learning to actually implicitly learn all the necessary features or cues that are important for making certain decisions. But once you actually fix that as an interface, you cannot learn these features just the same way we learn, for example, visual features for object recognition. So if this is not a neural interface, but it's just a simple, ROS message, then yeah, that sort of is limiting. Also, very often these are not probabilistic interfaces, and it's very difficult. Let's say if pretty much everything has uncertainty in this pipeline. So if I just kind of make at some point a maximum likelihood decision, say, well, this is my best prediction, and just give it down the road, down the pipeline, and it turns out that maybe there wasn't a good one. There's pretty much no chance to go back and make corrections. So ideally, the whole thing should be probabilistic end to end, and also learning features that are relevant. So discovering structure. Right? And yeah, the other important thing is that with this nice modular system, essentially it's a siloed development, and things are just falling between the cracks. So and actually we observed this ourselves in our development. So there would be certain improvements. We would have improvements to the tracker, but suddenly the whole system didn't work better, right? Because we had behavioral planner actually put in some guards to reject some of the noise from the previous version of the tracker. Now we have a better tracker, so we now have to go back and remove the rejections in the rules. We can make the rules nicer, but it's a very much back and forth and a lot of tweaking, and it's a difficult process. It would have been so much better if you could actually optimize it end to end, not having just independent optimization criteria for each module, but say, well, here's the optimization criteria for how we want the system to operate, how we want the car to drive, and now figure out how you how you tweak the parameters across the pipeline to do the best job. And so essentially, this is what the original architecture was doing with the monolithic neural network, was just figuring it out yourself, because you were training end to end basically means it's end to end optimization. But we can do that, right? We can actually fix these things. If we just make all these modules differentiable, then we can define end-to-end optimization criteria. So that's the sort of future vision, and this is Raquel Utterson is sort of pushing this vision within Uber ATG. I think this is quite fascinating. And so basically the idea is to say, well, there's probably more and more learned components, including planning and prediction, detection, tracking, and prediction. Clearly can be integrated, and actually planning should also be integrated. But it's not just a simple end-to-end network, because what's important is that actually we can recover all these intermediate models, if you want, that we had in terms of these bottleneck interfaces. We can recover them by encoders and decoders. So roughly you can think of it, it's almost like an autoencoder structure where you have latent representations, which are essentially neuron activations, but then you have encoder-decoder interfaces that kind of translate them into expert models or expert understandable models. So ideally, this type of system, now what it has this capability of discovering new representations, so it can learn representations. So this is how the sort of fixed inflexible interface becomes now more flexible, because it evolves as the system learns more about its task. But we also get interpretable representations, because through these encoders decoders we can actually map them into some understandable models. And we can optimize this whole thing end to end. All right, I think I'm gonna have to speed up a bit here to make some time for questions. So there is some work that, for example, Raquel's group has done in terms of demonstrating sort of this end-to-end joint detection, tracking, and prediction, but also like a integrated neural planner. And so I think this is all fantastic. One thing that, of course, I see here is that prediction kind of Well, it's something that lives really between perception and behavior. So prediction kind of is connected to perception because, let's say, if I perceive a child, then right away I start creating certain mental models of how that child might behave. I sort of set certain parameters into a certain policy that might be sort of used to predict the child's movement, which would be different, let's say, for an adult or an elderly person. But at the same time, predictions are really part of planning because, let's say in this old stack, if I just have a rule-based planner, it's very much reactive. It doesn't really think ahead and say, okay, if I do this, I think that the other agent will do that, so I will do this, right? So it's sort of kind of strategic thinking, like in games, right? So you really need to be able to actually put planning, prediction into planning. So it's really somewhere, this kind of division here is problematic. And so briefly, I tell you just some efforts that we've been doing in terms of trying to think about how to deal with learning of decision making, right? So it's clearly that sort of this expert system that was handcrafted, it was nice and kind of for a smaller system, easy to understand and evolve. However, extremely conservative. So I mean, like basically the way we engineer this is it's like if we were coming to an intersection, like let's say unsignalized intersection, we would just wait until everyone moved out and then we would just proceed. And so we programmed these rules like very consciously, so just to be kind of on the safe side. But we see that's sort of how the early prototypes are moving, and they're actually causing road rage. Like people actually been shooting into tires of these cars in Arizona. And so you can say, well, fine. I mean, road rage happens also with all sorts of other human drivers who might be more defensive. But fact is that robotic driving is robotic driving, and there's this. There are problems when the robot is hesitating, taking left turn for a really long time and causing big backups, and everyone being nervous. So okay, so let's look at what learning we could apply to make decisions. So one sort of simplest form of learning would be imitation learning. And so that behavior cloning is essentially what we've seen in the very first architecture. Let me just close here. The behavior cloning was this idea of just supervised learning of policy. Another way of doing learning would be reinforcement learning. So it's learning from sort of reward signals, and so there've been impressive results from we all know about AlphaGo, but also robot manipulators and legged robot motion and so on, doing backflips and so on. And we can also generalize from sort of single agent learning to settings where we have essentially multi-agent interaction. And so just very, very briefly, in reinforcement learning, you have an agent that performs an action and then observes some state changes and receives some rewards. And essentially, all it has to do is to maximize its sort of accumulated reward, which is typically somehow averaged and accumulated over a certain time horizon. So sort of to study this and see how this would apply to autonomous driving with now a group with students and collaborators in my lab, we've built this WiseMove environment, which is sort of a laboratory where you can try out basically applying reinforcement learning to different traffic situations, like in this little video here. So the system has all the ingredients you would need to do that, and it has hierarchical decision making. So it's an options framework. So you have maneuvers, and you have the lower level policy that does the trajectory implementation. You can use Monte Carlo tree search to both do like a runtime verification or to do exploration at training time, and it does deep Q learning basically as a representation of the value function. So yeah, I'm gonna skip that. I don't have time. So we try to actually do transfer of policies learned in this cartoonish world onto our high fidelity simulator with some success. But and also distilling some policies from that were learned. But let me just sort of summarize the kind of some of the high level insights. So first of all, it's been extremely hard to train using RL. It's very, it leads to lots of training episodes. So the fancy word for that is it has a high sample complexity. It's very tricky to get to converge, requires lots of tweaking of the reward functions, has a very high failure rate. I mean, if you get like 1% crash rate at that intersection, that's pretty good, considered pretty good. There is a whole research field which is called safe RL, but I think it's a misnomer. It should be called safer RL, or maybe towards safe RL, because it essentially has no guarantees, not even probabilistic. And but there's also one fundamental problem in the application of RL in autonomous driving, which is essentially if you're training an agent and consider everything else as an environment, well, you essentially have to have policies for all the other agents, fixed policies, right? And so you would have to have the models of how humans behave and how they drive and so on. And if you had that, you pretty much figured out the driving, right, problem. It's a bit of a catch-22. So that lag of these realistic human behavior models is a showstopper. And so I think, so we've been actually moving on to look at multi-agent settings. And so this can be then started using game theory, where we have hierarchical games with utilities, with observations that are partial and noisy. And most importantly, we can actually model bounded rationality for human agents. So we can actually have mixed populations of robots who behave rationally and humans who behave in a bounded rational fashion with different models of bounded rationality. I don't have really time to talk much about that, other than that basically from those games, we would then use equilibria as sort of the mechanism for prediction. And this can be used for planning, to actually do planning in a car, and actually you predict and plan at the same time, because you essentially say what to do for every agent. And you can also use this in simulation to basically simulate realistic human behavior, because what you do is you take these models and fit them into actual data. But these models generalize much better than, let's say, just pure behavior cloning applied to some collected traffic data. And so we've just recently submitted a paper where you can read more about how to actually model these games. And we've collected data set using drones in Waterloo on a busy intersection, and studied different types of equilibria or solution strategies to really learn what type of equilibria people actually strive for in actual traffic. And so that's work by Patricia Sarkar, one of my PhD students. All right, so just wrapping up. So we've got this modular end-to-end approach. That's sort of the future, hopefully, which means there's kind of this modular neural networks inside. Could be also interspersed with traditional algorithms, as long as they are differentiable, so you can actually do end-to-end learning. And you have these interfaces that actually create the models that you would normally have in the classical approach, so that and they are bidirectional, so you can also apply supervision. You can supervise end-to-end, but you can also apply supervision to individual sort of functions of the system. Now, this is not yet completely realized, and I think there is still pieces needed for this to be to work really well. So certainly, out of distribution detection is a big problem. So we've heard from Joshua Bengio, this problem of system 2 technology that's missing to generalize. It's not clear to me that whether we actually need system 2 just to detect. That's not clear, that's not settled. We definitely will need some form of reinforcement learning, but not the sort of simple one that I discussed. But we'll have to have rich reward structures. Will have to be combined with imitation learning to combat this problem of essentially high sample complexity. So very often by just showing agents something, how to do, it's much faster than letting the agent discover something. So it's that's important capability. Also being able to do counterfactual reasoning. So essentially like, the robot being able to dream or think about things through situations. Ideally even go and watch some movies and learn how to drive just from watching and thinking about it. All right, so that's it. I've got some examples about MDE for AI, and I guess I can talk maybe if there is any time for question, but just my take home messages. We've got, I think that expert models are definitely needed in AI-enabled systems, even when they are increasingly learning-based. Just because we have to represent requirements, we have to communicate with humans, and I think that's where the use comes in for our expert models. Now, what do we need for data model-driven engineering, which we could call maybe DAME? We need probabilistic models. We need uncertainty management. We need flexible integration with data, which is today very difficult, like having ontologies for all this traffic data that's annotated. Model discovery, so that we actually can improve the models that are being outputted by these encoders, decoders. Finally, don't expect a self-driving car to pick you up anytime soon, because it's a big question whether a system 1 technology can actually match human driving performance or actually outpace, even with massive data collection and engineering effort. That's what people are actually trying to do, or the companies are doing today. So I don't know. Okay, so that's it.
Right. Well, thanks, Krzysztof, for the great keynote. So we are kind of tight in time, but I'll make time to take a couple of questions. We actually have a bunch in. So the first question is by Femelis Michaelis. So he says that driving is also very modal. So like highway driving, high traffic, low traffic, industrial, there's all these modalities. And does it make sense to put this modality at the forefront of the architecture in terms of like the requirements, safety, levels of abstractions, and uncertain, and also in terms of the uncertainties you would be preparing for?
Yeah, absolutely. Just to say one thing that I said, we want to do these things probabilistically inside, but often, today we have to sample, right? And so, for example, when you do prediction, and the prediction modules would actually just sample a few possible future trajectories, and you would try to kind of have like maybe a couple just, but diverse, just to represent that multimodality. And of course, the more we can represent multimodal distributions, the easier the whole process becomes. Yeah, but it's very important.
Okay, so the next question is by Andrzej Wazowski. So it says on slide 17, you showed an architectural diagram with 2/3 of more of the space devoted to perception. Does this reflect where the complexity or amount of code is in autonomous driving? Decision-making and control were very small. I guess looking at kind of the percentages of these components and things.
Yeah, I would say today a lot of code is in perception. It's a very tough, it's essentially if you make a mistake in perception, then the rest is it's a foundation essentially. And so mapping is also part of that, localization. Yeah, there's a lot of code in that part.
Okay, so next question is by Thomas Toom. So automated driving seems to give quite some power to engineers. How to make sure that in this multi-objective scenario, example, comfort and safety are conflicting, that cars behave as it is good for humans or the environment as opposed to what is great for the driver of the car?
Yeah, I mean, that's a great question. There's a sort of a traffic system question, and you know, the focus here of my talk was just to say, well, how do I build one car that can drive? And then we have to, you know, start thinking about the strategic layer, not just the tactical and operational, but the strategic layer. And that has to be basically data driven and has to, you know, this is where the cloud systems come in into play, and all the interesting work on value-based design or value-driven software engineering. How do we represent values? How do we make them explicit? But also how we gather that. So just as an example, one of my master's students, Nicole Dillon, did a one together with Marco Lievsky. They did a wonderful experiment where what they did is basically they put biosensors on passengers. It was eye tracking, skin resistive response, and heartbeat rate monitoring. And so they were essentially then adjusting the driving style of the autonomous vehicle. So we're actually testing this in a closed course and modifying the planner's parameters. And we were comparing this with how the biosignals were responding. And so with this idea that you could actually have humans, you know, the comfort be sensed. Ideally, you know, we would have methods to do that for the passengers, for also people who might, you know, somehow interact also from the outside with these robots. Maybe we can sense this in other ways, just through computer vision. But I think that there is a rich environment to sort of, you know, think about these topics. So yeah.
So I think a related question by Rick Rappis, and also something that's related to the SPL community. So he's asking, how about adaptable levels of safety depending on the area the vehicle is driving? So for example, telling the system to be very conservative where there's certain safety envelopes when it's in the city and around people, telling it to risk it more in the highway. Can this variability be modeled on a very fine-grained level, kind of as a connection to the SPL community? What do you think of that?
Yeah. That's a very interesting question. So this was a master's thesis of Ian Colwell about 1.5 years ago, or 2 years ago. And so we came up with this concept of a ODD, or operational, operational environment monitor that would monitor not just the outside, but also monitor the health of the system. And let's say, you know, the scenario would be if you lose a long range radar, so maybe you cannot really drive autonomously anymore on a highway, but you can still complete the trip within a city. And maybe the car can actually go and plan the route in such a way that it can complete the trip without going the highway. So we actually, yeah, so there's a paper on that actually uses feature models to represent the ODD and things like that. But I would just say one thing, it's sort of challenging, and it's an interesting problem. I found it very difficult to sort of decide which of that functionality should be in the primary planning system that also has to kind of decide what to do and how to adjust to changes in the system, or to what extent it should be separated. Right, and of course, as you design safety, you want to build in redundancy and so on. But it seems to me that you actually pretty much want to probably the sort of primary driver be very much aware about all these things that are going around. So maybe you have a backup there, but yeah. So it's an interesting problem. You know, how to actually, you know, whether it makes sense to have it as a separate sort of abstraction, or whether it just becomes another state in the planning. Decision making. Yeah.
Okay, so we'll take one more question. Thomas Toom is asking that, so in school, he learned that it takes 2 points to identify a line, 3 points to identify a triangle. So it almost sounds impossible to identify the location of a car whose size and shape is unknown with 4 to 5 points. How is that possible?
So, well, it's a great question. I think it also takes context into account and certain. There must be just patterns. There must be just patterns that even if it's sort of unconstrained problem, it just makes its best guess. It's a prediction, right? And if it's seen enough of these cars in the distance with a few points, and we do actually put the bounding boxes on those because we can see them in camera, so we can actually put the bounding boxes properly, even though there is not enough points in the LiDAR. But it's just that you know, certain constellation of these things, you know, very few points. I mean, it's really just handful. It's capable of doing this detection. Yeah.
Cool.
There's
so
also information of
yeah,
intensity. I want to say it's not just the 3D, but it's also intensity. So that helps. So there's an extra dimension there. All right.
So we have a lot of more questions, but unfortunately we're out of time. So we will send those questions to Krzysztof offline. And
right.
I encourage you to follow up with him if you have questions. Thanks again, Krzysztof, for the very exciting keynote. And yeah, I guess we'll move on to the next part now.
Thank you.
Thank you.
Wait a minute.
Just to mention that the next item in this morning session is the announcement for models 2021.
Right. So
and right after we will have a quick closing of the edition of 2020.
hello. So I hope you enjoyed the video. So we are very pleased to announce the next models 2021. So first of all, I would like to, I'm Zheng Jianghu, that's one of the general chair for the next models. And I would like to introduce another two general chairs, Professor Ubayashi. Hello, Ubayashi.
Hey, hello. My name is Naoyasu Ubayashi. It's a great pleasure for us to host Models 2021 in Fukuoka. Fukuoka is one of the most attractive cities in Japan. We are looking forward to seeing many of you in Fukuoka next year. Okay, thank you.
Okay, thank you. And Kishi Sensei.
Yes, my name is Kishi of Waseda University, Japan. It is very pleasure for us to have the next Models Conference in Asian regions. And as Ubai Sensei said, Fukuoka City is one of the most livable cities in Japan. And we believe we will be able to have the very comfortable conference next year. Thank you.
Okay, thank you. So I'd like to share the slides. And wait a minute, where are the slides? Slides here. So we'll prepare some slides and give a short introductions of the next models. So can you see the screen? It's fine.
We have the presenter screen rather than the.
Oh, okay. I see. So so now it's fine.
Perfect.
Nice.
Okay. So this is a simple. So next models, as written in these slides, will be held in Fukuoka, Kyushu, Japan, from October 10th to October 15th in 2021. So here are some important dates. Well, this is very tentative, still subject to change. So almost the same as this year. So we have some deadline. I think 3 deadlines are very important. One is March 15, which is a submission deadline for tutorial and workshop proposals. Another is May 15, which is submission deadline for foundations and application track papers. And the last one is July 15, which is submission deadline for others, posters, doctoral and educators, symposia, demonstrations, and student volunteers and other events. Okay, so here we have seen the program general chairs, and I'm from Peking University, and Tomoji Kishi Sensei from Waseda University, and Naoyasu Ubayashi Sensei from Kyushu University. So we have program 2 co-chairs, Daniel Varro from McGill University, and who is a foundation track chair, program chair. And for application track, we have Shiva Nejati from University of Ottawa. And the steering committee chair is Jody Cabot, who gave us a lot of advice and suggestions. So the next models will basically be hosted by Kyushu University with a research group led by Professor Ubayashi, Professor Zhao, and Professor Hasatsumi and Professor Akame. So they were responsible for organizing the local organizers of this Kyushu, of the next models. So I think many submission details and additional information will be available soon. We're hopefully to make it available early December this year. So next, I would like to introduce some things about the Japan and Fukuoka venue. Okay, so I think Japan is quite an attractive country to visit. Safe, friendly, and I think you could enjoy Japanese food and Japanese culture. So this date, we hope that everything will go well, okay? And now Japanese government, you know, we will have a Tokyo Olympic next year. And now I think Japanese government has opened the doors currently, gradually, for business people, for business trip, for people to visit, foreigners to enter Japan. And I hope the situation will get better and better. And we hope to have a physical meetings next year. And about Fukuoka. So Fukuoka, this is a small map. It's a map of Japan. So you can see on the right is Tokyo, and middle is Kyoto, and on left is Fukuoka. And Fukuoka is the 7th most livable city in the world. Well, data a little bit in 2016, okay? 14th best city in the world. And what is perhaps a bit surprisingly is the 2nd most often international conference held city in Japan. So some people may think Tokyo, Kyoto, but actually the 2nd most often international conference held actually in Fukuoka. So we will have meetings in Fukuoka, or have models in Fukuoka Convention Center. Here I show some pictures there, including the conference rooms, outside outlook, and we have various kinds of rooms and very nice facilities. And the good thing is that this convention center is very convenient, about 15 minutes taxi from the airport, and also easy access from the city center. I have a small map here. And in this map, you can see Fukuoka Airport, somehow in the middle, or no, well, a little bit right. Only 6 minutes train, you can get to the Hakata main station. This is a sort of center of the city. And the convention center is near the sea, where you see 3 huts, okay, the huts on the left. This is the Fukuoka Convention Center. For distance, almost the same as distance between Hakata main station and the airport. So it is quite very convenient. And so we would like to welcome to Fukuoka. And so we will have a video later, which is some introduction about more detailed explanation of Fukuoka later. So before that, I would like to invite the program chair, Daniel, to say a few words about the next year's models. Daniel?
Yes, welcome everyone. I'm sharing my screen, not this one. Sorry.
Yes.
I'm I might be sharing the wrong screen.
Yeah,
is it fine?
Yeah, we can see it is a sort of full screen, a little bit smaller, but it's fine.
Okay.
Yes.
Okay, so interestingly, so anyhow, I only have 2 slides to share with you. One is the serious one, and the other one is not so serious one. So we will have we are accepting papers, your excellent about your excellent lines of research for next week, with the next year for the 2 main tracks, both the foundation tracks for research papers and new ideas and vision papers. And the practice and innovation track is accepting, again, industrial papers about reporting industrial methodologies and tools, case studies and experience reports. And the most important aspect from our part is that the deadline is expected to be middle of May. And as a further kind of invitation, you know, I like to play around with words in a playful way. So I have some very informal and not so serious advice for the authors, how not to get punished by the reviewers next year. So I warn you that all foundation tracks papers should be blinded, this time by the rising sun. You have learned from Zhenjiang's report that models and Japan is a peaceful place. So empirical studies should strictly exclude studies on empires or emperors. So certain time, this scalability studies should be executed, since we are going to Japan. on a pentatonic scale. And last but not least, you should double check your paper for the sake of completeness. So anyhow, we are expecting you to send and come to Japan next year, and I hope we will have an excellent conference, hopefully seeing you in person.
Okay, thank you, Daniel. So we'd like to welcome all of you to come to Japan next year, and we'd like to end this session with a video. Let me see which one. Maybe this one.
Fukuoka is overflowing with opportunity for your visit to Japan. It boasts the highest rate of population growth in the country and the largest ratio of young residents. Fukuoka hosts more international conferences in Japan than any city but one. Plentiful convention facilities ensure a successful meeting, and 35,000 hotel rooms provide accommodations to suit every need and budget. The city is brimming with one-of-a-kind experiences. People from around the world come to Fukuoka and leave with memories beyond expectations. Fukuoka International Airport offers efficient connections to Asia and the rest of the world.
从福冈通往海外的交通真的是非常的方便，特别是通往亚洲各国的交通，比如说韩国的首尔、中国的上海，到福冈的飞行时间只要1个半小时，比东京都还要近。从芬兰的赫尔辛基将开通到福冈的直达航班，另外国际各大中转机场，比如韩国、新加坡，都已经有直达航班通往福冈。由福冈通往世界各国的交通完全没有问题。
The airport and the convention zone are within a 2.5-kilometer radius of the city center. Get off the plane, grab your bags, and hop on the subway. In 10 minutes, you'll be in the middle of town.
Yeah, well, Fukuoka is a really compact city. The most obvious thing is the fact that the airport is so close to downtown, and almost everything else is in walking distance. Fukuoka has is a great relaxed atmosphere. It's just a wonderful place to walk around even on your own.
Fukuoka extends a warm welcome to organizers and participants alike.
People that is extremely outgoing. They try to let feel the visitor at easy. Attitude of the staff of the local organization that was extremely professional, competent, and very friendly, extremely welcoming also of all foreigners also, not only of course the local participant coming from Fukuoka or from Kyushu.
Meetings are made to order with everything provided in comfortable and efficient facilities. And that's just the beginning. Fukuoka and the surrounding area are filled with advanced industry and research institutions, adding to the environment for meaningful meetings. A day or a night on the town is an experience to be savored, with all sorts of possibilities for parties and receptions. Sightseeing, excursions, and food are close at hand. Fukuoka makes your meeting more than you imagined. Make it your destination for success.
Fukuoka is full of young people and universities, and is a booming research area, which makes it the best place for starting a new business. Also, Fukuoka has received much praise for being the most livable city in Japan. Be it delicious cuisine, abundant nature, or entertainment, you can easily find them all here in Fukuoka. Please visit our city. We hope to see you soon.
Your meeting place, Fukuoka.
So that's all for the announcement sessions. We are very much looking forward to welcoming you all in Fukuoka next year. Okay, thank you very much.
So a few words from Eugene about the attendance this year, and also to thank you all about your participation.
Yes, so thank you all for all your participation. You have been exactly 505 participants in the conference this year, so we're very happy to see that. Here I'm sharing some statistics that WUVA gives us. So we see, for example, the number of app downloads. So 94% of the people have downloaded the app. Doesn't mean they've been using it. But what's more interesting is if you see here the messages. So the average of WUVA messages in a WUVA event is around 1,200, and for models, you have almost 4 times multiplied this number.
And just to mention that this does not include the Q&A and chat in Zoom sessions. This is only the messages in the community section of WUVA.
Yes, yes, absolutely. And the number of community boards, the number of topics was 57, where the average is 14 in normal WUVA events. There was a lot of photos shared. There was a lot of meetup set up with over 100 attendees in these meetups. And this last number shows you the visibility of the sponsors. So how many times have someone seen a screen where the banner of a sponsor was showing? So that results in an astronomical amount of 351,000 views of the sponsors. So this is quite impressive. So the bottom line is to show that the models community is one of the most active out there, and we're very thankful that you do that. And probably some of the things you can see is on the app, we have a leaderboard. So it gives, there's kind of a gamification in WUVA. And we see here, they kind of rank and give points to the people who are the most active on the app. And here you see the standing. So thank you very much to all who have done that. Finally, so this here should go away. Yeah, finally, many of you have responded to the session feedback. So we got 223 responses for the session feedback. So thank you very much. We would just like to remind you to go in the survey section to give us the post-conference survey. This is very important. Until now, only about 30 people have answered it on 505. So we would really like to have your opinion on how the conference went and some of the questions that are related to virtualization. So thank you very much for attending models, and there are still 6 sessions left for the rest of the day, and we look forward to seeing them, starting with the most influential papers in the next session. Bye-bye.